my most favorite people. And Susan started off today commenting on how it's a time when molecular dynamics simulations can actually contribute to real biological questions. And I, for one, want to echo that. It's a very exciting time for us. I think, Andy started in this field some time ago. John and Benoit and I we're all three in Martin's lab approximately the same time, and it was one of those times when the Karplus group was really stimulating. We were going from the time when simulations were van der Waals argon spheres, really looking at proteins, and now today, in just relatively short time, we've gone to 1 million to 10 to the 7th to 10 to the 8th times bigger systems that we were looking at just at the time when Andy started with cytochrome C, and 2 picoseconds was an Nature paper with no solvent and no hydrogens. So it's really quite remarkable. So electrostatics and long-range coupling in Src-family a real system. So what I'm going to talk about today is it is only computational work, although we're also in the lab doing some NMR studies on kinases. Also a lot of fun. But today I'm going to talk about simulation work, and this is all done by these two wonderful people who have been in the lab. Elif Karemli is currently a professor at Boğaziçi University in Istanbul, Turkey. And He Huang is a student in the lab and is sitting right there in the third row, who has a poster over there. I'll talk to you about that later on. So the two topics are going to be something that we've called a switched electrostatic network, that I think is going to be a factor, a significant factor in the actual transition between a downregulated and an activated form. And in this last 1/3 or so of the talk I'll describe a long-range, what we think is involved in some of the long-range distance type regulation that, again, Susan mentioned at the beginning of today's session. So just to get started, the two systems are well characterized by crystallography. John and Frank solved this structure about the same time that Steve Harrison published the same structure. So John and Frank worked on HIC and Steve on Src. And this is in the downregulated form, and you can see that the thing about Src-family kinases is that they have these two SH2, SH3 domains assembled against the catalytic domain. This is the downregulated state. The activated form, also done crystallographically. First is just the catalytic domain alone in Wayne Henderson's lab, and then as the nearly full-length form in the activated state by this other group some years later, and they find that the SH2 and SH3 are actually disassembled from the catalytic domain, as John and co-workers, I guess several other people, worked out that the activated form would have SH2 and SH3 dislodged. Okay, so we're going to be looking at the difference between these two well-defined states. So the downregulated form, the activated form of the catalytic domain. There are many differences. We can look at the crystal structures and see them right away. There's a lobe-lobe distance that's changing. There's the activation loop that changes. And then there's this key rotation within the top lobe that John noted right away from the crystallography, where this helix rotates with the glutamic acid out to the glutamic acid in. And so these are key features that are different. The question is, what's important about these features? How does it work? How do you go between these two states? So looking at these differences in the A loop, you jump to the conclusion that phosphorylation is important. perhaps for ligand binding, substrate binding. But then when you start to probe some of these, and I don't know if Joe's here today or not. He's at home with the kids. Okay. So he did some very nice work, some kinetic work, that it's not always the case that A-loop phosphorylation is necessarily critical for activity. So you can have the unphosphorylated A-loop. So again, we're talking about the phosphorylation for the active form here and unphosphorylated for the downregulated form here. But when you look at the actual activity, you can get an active form without phosphorylation, and phosphorylation of that A-loop doesn't always affect binding. It does sometimes, but not always. So we're going to use simulations to try to figure out some of these key steps. I mean, if you were going to design an enzyme that has this conformational switch, how do you do that? What's the important components? And another feature for trying to understand this in more than just the two end states is something to do with conformational targeting of inhibitors. So here is a well-known structure between Gleevec that binds the downregulated form of Abel, but doesn't bind Src. An analog of Gleevec was found to bind Src in the so-called downregulated unphosphorylated form, but when the crystal structure was determined, this analog of Gleevec actually pushes, if you will, the equilibrium to this activated form. So now we have the unphosphorylated catalytic domain that looks just like it did in the original activated phosphorylated crystal structure. And of course, binding is not so trivial all the time. If you overlap these structures, you see that a molecule that's very similar chemically binds in rather different states. All right, so we can try to understand the conformational complexity of this, starting from these snapshots, if you will, that crystallography gives us. We might be able to make some predictions and understand how these things bind. So right now, we've described a lot of states. We're trying to understand them, explain them, and eventually predict them. So what is the pathway to go between these activated and downregulated states? Are there any intermediate metastable states? What determines the allosteric mechanism, this distance effects that we see in terms of controlling the conformational equilibrium? And how does all of that couple to catalytic function? So these are the big picture questions. Today, I will just talk a little bit about some of this, which is the switched electrostatic network we think is important in going between those two states. That is, it's going to be a determinant of this transition pathway. And then I'm also going to talk about some of the factors in this distal regulation involving helix C and a trip 26. Okay, so first, how do we do this? So to go between active and downregulated, this is a very slow process, okay? We can't just put it on the computer and simulate it for the most part. We'll just leave it there. So what we're going to do is use something called guided molecular dynamics, the kind of term guided molecular dynamics, where you push through an activated process. You know the two end states. You start in one, and you kind of move the system into the second. All right? And there are multiple ways you can do this. One of them is called steered molecular dynamics that Klaus Schulten has done a lot of work with. So if you start with an RMS difference of some value between the two states, A and B, you add an external potential that keeps it at that distance, and then you just move that external potential so that that difference, let's say an RMSD difference, starting at 5 becomes 4, 3, 2, 1. So you reduce the RMS difference between the two states. And you can do that in either using this harmonic restraining potential, or you can actually do it in a fixed coordinate fashion so that you demand it to be a certain value. This is using holonomic constraints. A somewhat different method is biased molecular MD, where you don't actually demand the difference in coordinates to be a certain value, but you start it at some value defined by A and B. The system has spontaneous fluctuations, and if those spontaneous fluctuations move in the direction closer to B starting from A, then you put up a potential so that you don't let the system go back. Right? So it's spontaneous movement without actually driving it. But it is pushing it in a single direction. Okay? So we've done most of our work, I guess, with this biased molecular dynamics. It seemed a little bit more gentle to move the system by just spontaneous fluctuations and then keeping it going in the right direction. More recently, we've looked at all three methods, and they generally produce similar results. Okay, so biased molecular dynamics. So we've done many of these biasing trajectories, forward and backward, activating, deactivating. And what I'm going to just tell you is something that we observe from these transitions. So what happens when you go between A and B. And there's a group of electrostatic residues that are interacting in each of the two forms. So I'm showing here the downregulated form, and there are interactions, electrostatic interactions, defined by the crystallography that show, for example, this interaction, and this interaction. So we have electrostatic pairs. If you now look at the activated form, those residues have switched electrostatic partners. Okay, so for example, lysine 295 in one state binds aspartic acid 404 in the Src kinase numbering, and then it switches over to bind with 310. Okay, so there are these set of interactions in each state that are different, but involving the same group of residues. And if we look a little bit more closely, these residues are well known, shall we say. The aspartic acid is from the DFG loop. K295 is this beta-3 lysine that is also known as kind of the kinase dead mutation. Blue 310 is the helix turning in and out that I discussed earlier. And then RH409 is on the activation loop, and D386 is the catalytic acid. So here is our set of electrostatic interactions. What I'm suggesting is that these interactions are not only important in the ground state, but they're going to be important in actually transitioning between the two states. All right. So our analysis here is not on 50,000 atoms, or 50,000 sequences, it's only on a few sequences, but these are absolutely conserved to my knowledge. These residues are absolutely conserved with the exception of RH409, which can be an RH or a lysine. Okay, so what am I talking about? So what I'm telling you is that this electrostatic switch has a three-way interaction that goes to a two-way interaction. And I'm going to show you a short movie first to illustrate what we're talking about. So here is if you focus on blue 310, it's starting here, hydrogen bonded to the A loop, and it will become hydrogen bonded to the lysine 295. No, it's not. Okay. So. Is it in the same directory now? It's showing here. Okay. All right, so what you would have seen is that this fluctuates around. The loop actually moves quite a bit, yet this interaction stays, so I can show you right here. And then it basically hands off. So the main chain moves quite a bit, yet the side chains are anchored together, and then the lysine 295 moves from being the blue 310 hydrogen bond in there to the K295. Okay, So we've looked at this in a number of trajectories. So if you see something once, it's not particularly significant. But if you look at these trajectories, many of them, you can see it over and over again. So the way we do this is to just plot the time series. So this is the interaction of glue 310 with the activation loop. And it's a short distance. Then as the trajectory progresses, the glue 310 switches to K295 in this very short period of time. Okay? And then if you look in the reverse transition from active to inactive, this starts in with this interaction, and then in a very short period of time hands off to the other residue. All right, and then you can see this with this second switch, if you will, based on centered on Y416, starts in one direction, hands off, and goes to its second partner.
Well, Carol, here your 416 is not phosphorylated.
That's right. That's right. So this, if it were phosphorylated, it would probably be even stronger, right?
Yeah, it's not strictly a salt.
That's right. So if we do this on multiple trajectories, forward, activation, inactivation, we use different methods, biased, targeted, steered. We see this switch, okay, where they're going from one, handing off to the other in both directions. So what does a non-switch type interaction look like? So if we look at similar kinds of time series for other pairs, so here's one that I tried to pick out from the structures. You can see that in some trajectories you get something that might look like a switch, but in many times these things just kind of randomly, move away from each other, come back, and you don't get this nice switching off or handing off in a short time period over the trajectory consistently with multiple runs. All right. So how do we test this? All right. So the kinetics now has offered us a way that you might ask, what role does electrostatic interactions play in conformational transitions? All right, so the first thing that comes to mind is ionic strength. If you have an electrostatic interaction, you increase the ionic strength, the interactions are going to go down. So the kinetics of Src kinase activation offer us the opportunity to look at this lag region, which Todd Miller showed to have to correlate with autophosphorylation. So this, if you dephosphorylate the enzyme, look at substrate phosphorylation, you get this lag phase where it's a very slow, slow phase, and then it takes off into a more rapid, fast phase. So this initial lag phase was shown by Todd to be conformational activation. All right, so it can be, I'm showing it here as a simple kinetic scheme of one enzyme autophosphorylating a second enzyme. Okay, and then the fast phase is going to be substrate phosphorylation. Okay, so we're going to look at this lag time as a function of ionic strength.
So Harold,
yeah.
You have kinase 1 phosphorylating, kinase 2 not kinase 1 phosphorylating itself?
Kinase 1 and 2 now are two molecules of the same kinase.
Yeah.
Okay, yeah. So, right. All right. So if we look at that lag time as a function of ionic strength, we see, in fact, that at higher ionic strength, the lag time goes up, consistent with a longer time for conformational activation. Okay, but you have to also consider that there are other things going on in this process, right? So you have the bimolecular encounter complex, as well as phosphorylation and conformational activation and release. So we're going to try to rule out all of these other factors as well as possible. So if we first look at the concentration, enzyme concentration dependence, and extract relate back to zero concentration, we can remove the effect of the bimolecular encounter. In fact, that's what Todd was using to show that this is, in fact, trans-autophosphorylation. So this red line here then is removing the enzyme concentration effect. And in fact, you see that the salt dependence has now actually gone up. And that makes sense because the bimolecular encounter of two similarly charged molecules is going to be electrostatic repulsive, so it's actually in the opposite direction of electrostatics, promoting the conformational activation. So we get a very nice steep slope there. Okay, so in terms of what else the salt dependence could be due to, another possibility would be the SH3-SH2 disassembly. So if we look at catalytic domain versus full length, we still see a strong salt dependence. Okay, so it's not just SH2, SH3 coming off of the catalytic domain. And here, if we look at the fast phase dependence on salt, so that's peptide substrate effects of salt, we see absolutely no dependence whatsoever. So for that, we interpret to be that all of the other stuff going on, the chemistry, binding, product release, has no salt dependence. All right, so we're left with the conclusion that there is a salt dependence on conformational activation coming from the catalytic domain. And so that's completely consistent with this handing off, if you will, of this set of electrostatic residues during the transition process, not just the two in space. Okay? So that's our conclusion with respect to the switched electrostatic switch network. And we're trying to do some additional computational and experimental work to look at that further. All right, so now let me jump to the second part of the talk and ask about some of the distal regulatory effects. And the idea here is that, you know, catalytic domains are regulated in different ways, and in this particular case, we have SH2, SH3 coming off of the catalytic domain, and a question then is, how is this allosteric, what's the mechanism for this allosteric regulation? And we have some clues already that from mutagenesis work, and now we've seen a lot of nice information here today about helix C, that it's going to have something to do with regulation in this end lobe and SH2, SH3 contact through a tryptophan 260. All right, so how have we looked at this? Recent work, and this is the Huang's work, we've taken a little bit different approach. So bias molecular dynamics is a very, let's say, linear pushing of the system from A to B. We wanted to use something that gives us a little bit more sampling. So you sacrifice for the resolution of the model in this type of work. So what she's done is to look at a double-basin GO model. So this is a simplified model where instead of all atom representation, we have a single C alpha. The GO model defines the force field in terms of the tertiary structure. So we have a force field which guarantees a minimum at the two structures of activated and downregulated kinase. So that's represented here by this potential energy for the activated form and for the inactivated form. And we use this exponential averaging of these two minima in this form here to provide access to both wells through the simulation. So we have a very low resolution model, and we can use this type of exponential averaging to actually go between the two wells. We don't want to just freely sample, so we're going to use something called the string method to actually map out how to go between these two wells. And the string method is was, I think, primarily developed by Eric Van den Eyden and Chikoti.
It's Eric.
Eric.
It's
Okay.
really Eric who did that.
I'm not going to go into the string method. I'm just going to try to briefly describe what it is. And in order to do that, I've stolen this picture from Benoit's recent paper in JPC. So the idea is that you know the two end states. So we call these our two end states. We're going to define an initial path in some conformational space of collective variables. Here, Benoit has done something in only two variables, and you have two wells. And if you call those two variables your collective variable in space, the idea is to find the best path to go between those two wells. You start with an initial path, shown here in black, and then you iterate multiple cycles and eventually converge to the most likely path between the two states. Okay, so you sit and you sample at each node position in conformational space and find the best path.
Just as a quick question, is your protein set at the minimum in each of these, or do you allow fluctuations within its own basin?
You have restraints on the system so that it will fluctuate within those restraints. But this is, I should emphasize that this is in a collective variable space. So this is not all atoms in this collective variable space. So you sit at each node and then you sample, and what Benoit's clever idea is to use this initial sampling in what he calls swarms of trajectories, where you sit at the node and you launch many trajectories for very short time periods to actually sample locally and then eventually converge from the black to the red. But the collective variable space is small, not 3n degrees of freedom. And in our case, Hoa has selected a set of 168 internal distances to define these two wells between the active and inactive form. So what I'm going to show you in the next slide is going to look a little bit scary perhaps, but what I'm going to show you is that at each node...
Carol, again, what's the collective coordinates again? You said all this distance, how do you add that? They're just add together? How you define that?
Yes. So you have 168 distances, internal distance, C alpha difference.
But it's just the addition of them.
Sorry?
So the coordinate is a linear combination of all...
No, it's not a one-dimensional coordinate, it's a multi-dimensional collective variable.
It's a multi-dimensional collective variable.
Coordinate. Still a coordinate. It's a combination of all these things, but still a
No,
coordinate.
but she's doing this string method in a dimensional space of 168.
Yeah.
So she's finding a path in a 168 dimension space.
Right. You're optimizing, though, at each node in 168 dimensions.
Okay.
And, yeah. All right, so imagine sitting on this node now, and you're starting at some value of, let's just call this coordinate 1 and coordinate 2, and then as you evolve, each node has its own evolution of those collective variables. And that's what I'm going to show you on this next slide. So each node, this is the initial starting point now for Src-kinase. So at each node, the distances are some value, and the initial cycle is to just linearly interpret 20 nodes to move between the two states. So I have 168 distances. I linearly change them from active to inactive, or inactive to active, inactive to active. That's my initial coordinate, and now I'm going to evolve this under the string method and sampling. And the question then is, how do each of these individual distances change as a function of going from inactive to active? And that's what's shown here. So cycling through 200 iterations, how does the molecule move? And so this is a structural coordinate, and this is, let's say, the position along the path. And the two interesting features of this is that we see that the distance at each of these individual 168 distances changes in very different ways, right? So you see some of these go up and change and then come back down. And in particular, there's a set of distances that are all changing together at about this point right here. So there's a collective motion that occurs at this point here. So what is that set of collective distances? Do you know, Benoit?
No, I'm eager to find out.
Yes. It is helix C.
Yeah.
Helix C. No. That's what we've been hearing about for the last 2 days, right? Is helix C. So here are the distances that are mapped right here, if you can see them. And Hood has a variable here that, let me just say, it measures, it's a metric to describe how far along the progress you are between inactive and active states, all right? So if this value E is close to 0, then your structures at each node look like the starting point. And as this value becomes, whatever this is, it doesn't matter, plus 60 something, then you look more active-like. So at each node, do I look like active or inactive? And you can see that there's a sharp change right here where this collective motion occurs. All right. So the point at which basically you're probably jumping between the two wells in that double-basin build model is where helix C rotates.
Is that the mean of all those cycles?
Sorry?
Is that the mean of all
This is this value here?
Yeah.
No, it's actually calculated from this last cycle, but it's the energy of the system for all of these distances within the collective variable. Okay, so we're now going to jump back to biased molecular dynamics and all atom models and look at what helix C, how helix C is being controlled in Src, we think. So these residues have been mutated and shown to impair regulation. If you look at the crystal structure, and John pointed this out in his original, John and Frank pointed this out in their original paper, the TRIP260 has these very different structures lying right on top of helix C. So what I'm going to say is that by looking at the crystal structure, they're absolutely right. Tying together this information about regulation and crystallography, TRIP260 does seem to be a key component in this control of helix C. So the position here's our kind of usual way of looking at the kinase. And on the back side, if we rotate it around, helix C is here, and TRIP260 is lying on top of it there. So we did biased molecular dynamics on the fully assembled protein with TRIP260 either in the reaction coordinate or not. All right, so biased molecular dynamics, remember, is that one that you have an RMS difference between the two end states. That RMS difference is over some set of atoms. If TRIP260 is in that RMS difference, along with 300 other residues, we get results that look like this. So this is the RMSD to target of TRIP260 going between these two states. This is alpha C going between the two states. And you can see that there is kind of this position where TRIP260 moves and alpha C moves. This is our switch residues. Coming back now, alpha C contains one of the switch residues, blue 310, and it switches between these, the lysine and the A loop 409, and it switches, of course, right where alpha C rotates. If now all I do is remove TRIP260 from this RMS coordinate, which has again, 300 other residues in it, remove one residue, and the behavior is quite different. So now, trip 260 isn't pulled to the other state. That's not surprising, but alpha C never rotates, and we don't get the switches in the interactions of those residues. So basically, it's like trip 260 is locking helix C in position, and even though the rest of the molecule is being pulled to that second state, without trip 260 going, it doesn't switch. Okay? So our conclusion then is that, yes, as you might expect, based on a lot of the structural results, helix C is key, and its interactions with something are going to be key in promoting that allostatic regulation, which is connected from something in contact with helix C rotation, and then this electrostatic switch, which then communicates that rotation of C to the A loop and the rest of the molecule. All right? So then what I told you is that we find this set of electrostatic residues which jumps between what the crystallography's end states show us, and that it's important in actually transitioning between those two end states. And that secondly then, this distal regulation is coordinated through alpha C, and we can demonstrate directly that trip 260 is important for that long distance communication through alpha C, which then goes to the A loop. And then finally, let me thank Elif and Huang Che for all of their hard work in this project. And we're also collaborating with biologists and Bob Steele, who's also very interested in string methods, and Todd Miller and his student at Stony Brook for their kinetic work.
Carol will be happy to answer any of my sister's questions.
So maybe you're the perfect person to figure out why Bud 32 can work without that two-time residue.
I was wondering about that.
Put it through your pipeline. Maybe it won't. If you
It's got to be in, though, right?
Pardon?
So I guess the question was, Bud 32 does it actually activate, or is it always just sitting in an active form?
It makes no difference. The activity, pilot activity, appears to be unperturbed.
Could you speak up a little bit, please?
So, Bud 32, when you mutate the glutamic acid residue, nothing happens. So I'm just curious, how would it form in terms of that, your electrostatic switch?
So I wondered about that when you showed that it's an A mutation. But does Bud 32 activate? I mean, is it always in the active state and you don't need rotation because there's no regulation?
Okay.
I have a question here. Actually, when you were showing your dual goal model and the one figure that you have, I'd be very interested to see that binned out into patterns, whether or not you, because what we've seen with folding work is that when you actually get that kind of data, you get one thing when you average, but you can actually bin out into different patterns, and perhaps there's multiple paths, like predominant paths that you go through. One where you have to get that initial activation barrier traversed because of the starting material, and then a secondary one where something else happens later on.
So
Because if you go back, at first look, it looks like a mess, but when you look at it, there's groups within those.
oh, I see what you're, okay, I misunderstood what you're getting at. You're talking about
All the way back to your full go.
that, yeah.
Yeah, I see definite patterns and maybe some backtracking that might be occurring. Something happens, has to undo itself and then move forward.
I should have premised this, and I don't know if we even really want me to present this, because these are very preliminary data, but they were so interesting I just couldn't resist. But there are many things that we need to test with this, and
it's really interesting. I mean, this is exactly what we see with the folding. And then you bin them out and you see that there's patterns coming up. Well,
Actually, I'm curious.
Everybody's coming up.
I'm curious about it because it appears very interesting, the results, and I think they make sense. And I think what makes curious is that probably when this helix C does this big jump, on our notation, since the entire helix cracks and reform, you don't have something that goes elastically from one to the other. Because see, there's a lot of strain left on that helix, and so when you do this big switch around that you say require the helix to go around, my feeling that you go through something that cracks completely, get partially unfolded, does the switch to retain the strain, and then refolds again when it gets back there.
In our case,
Yes.
there's no reason for it to do that.
It looks
But I
like
will do it. You believe it can go just elastically. But there's lots of other, there's some strain on that. If all the control is on that helix, I believe there's some strain there. I'm just curious, just
It looks like it, Carol, and you can get that from a Go model.
I'm not sure why you think it would unfold though, because it could easily just.
you have contacts here. The helix is formed on both ends. It's not like you have it's not like you have like you have a hinge on each point, and the thing just switch on those hinges, and you have this entire cylinder in the middle. I would doubt that's the truth of it. I think people draw too many hinges into the system. I hate the word hinge, so I just say when you do the careful atom to check it.
Okay, we have a little challenge here. I think John Luigi had a question.
Yeah. So you use this bias molecular dynamics to reach basically the string from A to B. My question is that with a regular program, how probable is it to reach the two stages? So do you really need to do?
You mean to just do equilibrium MD?
Not, yeah. So it's impossible.
So in our hands, we never get there, but
Not to get at least one transition.
yes, there you are. These guys, I'm told,
So,
no, we never see it, but we do nanosecond trajectories.
so we actually simulated that transition with unbiased MD multiple times in Src, in Able, and in EGFR. So we've seen that the helix rolls out, and the glutamate break with the lysine of the beta suite and form the alternative solvers with.
So I'm not sure why, but I mean, we never see anything like that. They're extremely stable. I'm sorry?
How long was the simulation as the question?
Oh, so we're only doing nanosecond level. Oh, your simulation.
It's about 150 nanoseconds, and it involved perturbation on the DFT to knock. Well, actually, not in the case of EGFR. In the EGFR, you can just run and you don't do anything, it just come out. In Able and Src, you have to introduce a perturbation. In this case, it's a combination of the DFT. Which I believe disturbs the spine because the phenylalanine coupled with the aspartate, you alternate the aspartate, you perturb the phenylalanine, you perturb the phenylalanine, you perturb the spine, and this thing come out. And anyhow, so then this tryptophan 260, that's spot on. That's what you said.
So I kind of heard, okay.
Sorry.
I was just going to say that I'm surprised that you see it in 150 nanoseconds, but I didn't know that you
always have the help of bad forces.
I mean, I think this is where NMR has to actually come in and answer some of these.
Actually, I did it with two forces because I'm not sure where it is. One was I used OPS and used.
Okay, you have a question?
Yeah. So in a different question or a different topic, in those ionic strength experiments you did in the lag phase, my recollection is that the way those things are done, and maybe John could comment, is that you typically have the full-length form, and then you add either a proline peptide or a phosphotyrosine to sort of turn the process forward and allow the thing to get activated. If that's the case, is it possible that the ionic strength is contributing, changes in that is contributing to a number of those steps that lead to opening up of the kinase before you get into the sort of intricacies of the of the glutamate.
The opening up of the kinase.
Yeah.
So it's
Or the opening up of the-
dephosphorylated, right? So you
But
treat
is it tail phosphorylated at that point?
No.
So is this just the kinase
Yeah,
domain?
Yes.
So it doesn't
No,
have
no,
the-
so it was done both ways. The full length and just the kinase domain.
And is the lag phase the same, independent of
Okay.
No,
that?
a little bit different.
There's such fascinating questions here, but we need to move on.